here. Fantastic. Well, morning. Welcome to the reinforced concrete class. As usual, very excited to be here talking about the next design. And just want a quick recap what we have learned so far. So we have learned the analysis of singular reinforced beams, right? So analysis of singularly reinforced beam. Okay. Analysis of singularly reinforced. Okay. Now, what does singularly reinforced mean? One layer. Well, now I wouldn't say one layer anymore, but tension reinforced in the bottom, right? So if I draw my section like this, I only have tensile reinforcement at the bottom. Okay, there's no compression, okay? So this is called singular reinforced, okay? So recall what we did. So we did the strain diagram and get a compressive strain that is 0.003. You should know this number by now if you haven't. Now the yield strain of steel, 0.00207 for grade 60. Okay? And then we get the stress distribution and we say we need stress. So we have a block on top, and this is A, which is actually beta 1C, and C is right here, okay? And we have a tension coming from here. So that is the concrete compression and steel tension, right? So of course, Mn equal to ASFY, okay? And D minus half A. D is basically the depth of the beam. And when we say depth is from the top to the center of the bar, okay? And A is essentially the effective compressive zone. So that is the distance between the tension and compression, okay? So this is the analysis of singularly reinforced section. For doubly reinforced section, recall things a little bit different. I still have the section right here, but instead of only the tensile reinforcement, I also have compressive reinforcement top. So in the strain diagram, not only now I have the compressive strain in the concrete, which is right here, 0.003, okay? We also have tensile strain here, okay? And compressive strain here, so this is epsilon S prime, this is epsilon S, okay? So this is a new strain distribution. And keep in mind that we want this to be bigger than yield, so epsilon S, bigger than yield, and preferable if it's tension control, we actually want it to be larger than 0.005, so we have a tension control, okay? And for the compressive reinforcement, we want the strain to be smaller than the yield strain, and hence, I will have an equivalent stress distribution as before, a rectangle. So this is the Winnie stress block, and this is A again. So I have a concrete C. But don't forget now, I have a steel compression CS as well, right? So that's from the steel, and I have a tension from the bottom steel. So with this, the equation changes slightly, right? So now I have to make sure my compression equal to tension, that's first, and then Mn is different, right? Mn equal to ASFY. Okay, D minus half A, this part stays. This part stays, right? That's the, shouldn't write this way now. Should be the compression side, right? So it should be CC, which is the concrete compression, multiplied by D minus half A. Okay, so that is this distance right here. Okay, plus, all right, plus CS, multiply the distance right here, which is D minus D prime. D prime is the depth of the compressive reinforcement. Okay, so comparing these two equations, I'm gonna put these two equations side by side. For singular reinforced, right? For singular reinforced, it is this fellow here. For doubly reinforced, is this fellow here. So comparing the two cases, singularly reinforced, doubly reinforced, okay? My moment capacity calculation is different. So comparing to before, I have additional component, right? Contributed by the compressive, contributed by compressive reinforcement. Okay. So that is the difference. I still have some people in the waiting room. That is the difference between the singular reinforced section and doubly reinforced section. Okay, so there's a slight difference. Now, coming to the design, right? This is the analysis we talked about so far, right? We went through the whole 9 yards stress distribution, how to calculate the stress reduction factor and MN and get the strength out of it. And we talked about how we're gonna do the design for the singular reinforced section, right? Design for the singular reinforced section. So let's go back, right? Let's go back to see a design for a singular reinforced section. So we went through the design process last time, right? We went through the design process last time. So quickly recall, right? So this, I think this is analysis. So where's my design? Okay, here's my design. So start from a section. This is from last time, lecture notes. Start from a section, okay? I have bars at the bottom. Okay? I don't know what is the reinforcement, but I know the section. So this is called design a reinforcement with given section. Design a reinforcement with given section. So I use this equation mu divided by phi fy, okay? Mu divided by phi fy, okay, I'm gonna use a marker. So to get this AS estimated, But the problem is, since I don't know the location of the reinforcement, I'm going to use an estimated, okay, which is 90% of the depth, 90% of the depth of the beam, okay? So with that, I can proceed to calculate my AS. A side note, we talk about this. For a singular reinforced section, one layer, the depth equal to a height subtracted by the concrete cover, which is 2.5 inch, okay? So now we estimated AS, okay? Got some value here, okay? We use this AS to reversely calculate the effective compressive zone A, to calculate A. Once I have A, okay, I go back again, plug in right here, this equation right here, where I have the actual A, right? And recompute my AS. Once I recompute AS, I can select the bar now. To make sure I have enough. So from last lecture, we say we're gonna select 2 number 9 bars, okay? So the provided reinforcement area is much bigger than the required, okay? So once you select the bar, the situation changes. You have a cross section, you have bars now. So the problem turns into analysis problem again. The problem turns into analysis, right? You need to proceed to do analysis like so, this we did before, okay? The whole thing, right? The whole thing. And eventually got my strengths for the section. And then we compare the strengths, right, to the applied moment to make sure our design is adequate. Okay? So this is kind of recap of what we have done so far. Okay, so design a singular reinforced section with known section. Essentially, you're just designing for the reinforcement, okay? Designing for the reinforcement. Okay, so last time we stopped right here. Okay, and we have a cantilever beam, right? We talk about this, we have a cantilever beam, okay? Now, since we have a cantilever beam, I have a distributed load, and this is from self-weight. Oh, I think I write it down here already, right? It is from self-weight. Okay, and we also show that it has a concentrated live load of 5 kips at the end of it. 5 kips.
Could you scroll back up for a second?
Up or down?
Up just a little more.
This is previous notes.
All right, thanks.
Okay. Do you have them, Marshall? Can you see them from File tab?
No, I just my internet died early last class.
Okay. Well, make sure you download all the notes from File folder, okay? From the tab, all right? If you have problem access to, can you access to email, Marshall? Your internet is working at all?
Sometimes.
Are you able to get on campus or you're off-site?
Off.
So you don't have any internet at all?
No, I do. It just doesn't work sometimes.
Okay, so I can send you a zip file with all the nodes included, okay? So in case you cannot log in on Canvas, all right? But make sure you have all the nodes, okay?
All right.
All right, good deal, okay. So coming back to the cantilever beam, okay? Coming back to the cantilever beam. Now, we have the dead load from the self-weight of the concrete. We have a concentrated live load, and we're going to design a reinforcement for it, okay? So last time I asked the question, question is, which configuration should I go to, right? A or B, okay? I think Mike already answered the question, but I'm just gonna ask again, okay, in case we forgot about it. And my next victim is gonna be JD, Mr. Crawford.
Yeah, Nate.
Hey, how are you doing, man?
Doing great. How are you?
Not too bad. So recall, we said this configuration of reinforcement, right? So which one should we go for, A or B?
B.
B, right? Because it is negative bending, right? Negative bending, great. Okay. So remember, always put the bars, right? Always put the bars. Put the bars on the tension side, okay? On the tension side first. Okay, and this is good for singly reinforced section, okay? Singly reinforced section, okay? So what to do, right? What to do sounds so complicated. How do I know this tension part, right? Mechanics material, right? You take a bar, you take a beam, and you load it, right? Imagine what's gonna bend, right? When it's gonna bend like this, so this is a cantilever, and it's gonna bend like this, naturally the top fiber is gonna be stretched, right? Stretched, or tension, right? Tension side. So the bar is gonna put on top, okay? So if I have a beam, just a quick question, if I have a continuous beam, simply supported, but cantilever this part, a horrible drawing, okay, let me redraw it slowly. So I have a beam, and I have a support like this, okay? And I say I have a distributed load on top, okay? Now I need to know which location, right? So I have two locations. This is location 1, I call A, and this is midspan, location 2, B, right? Section B, okay? So this section right here, I'm gonna have a cross section, and this right here, I'm gonna have a cross section. Now the question is a little bit hard now, so pay attention, okay? Pay attention, all right? So the question is, for A, is the bar gonna be on the top or bottom? And for B, well, the bar is gonna be on top or bottom? Okay, so which configuration we're gonna have? Brett?
Yes.
Hey, buddy, how are you doing?
Good, how are you?
Great, great. So question here, right? So I'm gonna let you take question number 1. For section A here, will the bar be on top or the bar will be on the bottom? You still there, Brad?
Yes.
Okay. You understand the question? Should I repeat the question?
Could you go over it a little bit more? I'm trying to think about it.
Yeah, no problem. So I have a beam, right? The beam is supported at, say, location 1 and support at location 2, okay? And the beam stick out a little bit. So I have a cantilever portion here. I have a simply supported portion here, okay? I'm picking 2 sections. One section is at the support. I call it section A. And one section is right here in the middle span. I call it section B. I'm going to put the bars in them, okay? I'm going to put the bars in them. So for section A, should I put the bars on top or should I put the bars on the bottom for single reinforced section?
Would you put them on the bottom?
Why? Okay, that's the answer. So bottom, why?
Because you're right next to the reinforcement.
What do you mean right next to the reinforcement?
Or you're right next to the support.
Next to support, right? That's the rationale, right? Well, yep. Unfortunately, Wheel of Fortune this time, that's the wrong answer, okay? The correct answer should be on the top, okay? But let's take a look at why it's on the top, right? So that's a good attempt. You said as a support. Yes, it is at the support, and that is the reason. And that part is your right. It is on the support. So I skipped the step, is the moment diagram, Okay, it's a moment diagram. So when you decide to judge which location the bar is going to be at, you need to draw the moment diagram first. Okay, so from here, I have a support right here, support right here. Okay, and given the distributed load, I know the moment distribution looks like this. Okay, so this is positive bending, and this is negative bending. Actually, should I draw a bit differently? Reverse flicking point. Okay, this is positive bending, and this is negative bending. Okay, since it is cantilever, here on section A, here is actually a negative bending. That means tensions on the top. Okay, tensions on the top. And observing my section B here, it is actually a positive bending. Means tension is at the bottom. Okay, so essentially, when you decide to put a bar, draw the moment diagram first. To differentiate, is it positive bending or negative bending, and put your bar in corresponding location. Okay, so every time you want to judge which side you're going to put your bars on, take a look at the moment diagram. Okay, all right. Now, quiz. Austin, Mr. Horscamp, Austin.
Yes, sir.
What are you doing, buddy?
I'm doing good. How are you doing?
Not too bad, apparently. So I'm picking a section C. Can you see it?
Yep.
Okay, so this section C here, I'm just going to draw a section here. So my bar on the top or bottom?
Bottom.
All right, good answer. Why?
Because the tension is in the bottom.
Right, positive bending. Right? Good call. Okay, thanks a lot. So that's that. All right. So naturally, okay, I'm gonna call my next victim Daniel. Yep. All right. So your turn. Section D here. Top or bottom bars?
Top.
All right. Why?
Negative bending, so the tension's going to be topside.
Got you. All right, thank you very much. Good answer. So I'm going to drill you guys to death on this because you see this in exam again, okay? And it's vitally important, okay? It's vitally important. You need to know which bar, which side you have to put your bars on, okay? If you still haven't gotten a clue, go back and review your mechanics and materials a little bit. Get familiar with the moment diagram and judge from there, okay? All right, so that's so much about the location of bars, okay? Location of bar, but we're not talking about here today how we're gonna generate design. We're gonna go specifics, okay? So I'm just gonna drag this. Okay, I'm just gonna drag this lower somewhere, okay? Actually, you know what? Let me just cut it. And I'm gonna paste this somewhere so you still have it. Put later, okay? I don't like that. 7. Okay, let me paste it here, so we'll see it later. Okay, all right. So the focus today is still we're going to solve this problem, singular reinforced section problem. Okay, so let's just walk through with me. Okay, shall we? Let's walk through with me. First, now this is the final quiz, right? What is the dead load? So how you calculate it? And now we said the section is going to be 12 inches. If I remember correctly, it's going to be 12 inches in the width, 12 inch in the width, oops, and 24 in the height. Okay, and the dead load simply can be computed as 150 pounds per cubic foot. Okay, and multiplied by the section area. That is 12 inch, multiplied by 24 inch. That is area. Okay, that is area. Ooh, this to be consistent. Okay, and I want to convert it back to foot, so this is 144 inches per foot. Okay, inches per foot. So can I get a quick calculation here? So omega D equal to, let me do my calculator and while you do your weight. Mr. Compton, you there?
Yeah.
Can you give me a quick number to help me out here? We got 150 multiplied by 12 multiplied by 24 divided by 144. What you got? See what we got.
Should be 300.
300. Great. 300. Okay. What's the unit here, sir? What's the unit?
Pounds per foot.
Okay. So that is the distribute that load. Distribute that load. Okay. I'm very happy about it. I'm very happy about it. Okay. So let's take a look at the beam now. So I have now the beam, and I have a distributed load. Okay. Distributed load, and that is omega d equal to 300 pounds per linear foot. Linear foot. And I have a concentrated load P equal to the slide load equal to 5 kips. Okay, 5 kips. All right, so I'm going to sum the moment. Jack, Mr. Meadows.
Yeah, I'm here.
Hey, how are you doing, buddy?
Good.
All right, so section A at the fixed support, section B at the free end. Which section will be the critical section for my design, A or B?
Section A.
Exactly, right? So that is the critical section. Thank you. And now I want to sum the moment, right? So not too hard, so just simply support it. So I got a positive, I got a negative bending, which is this way, okay, plus a negative bending and the other triangle, right? So it's going to be constant, okay? And I know this value here is omega d multiplied by L, right? And then that's the distributed load. Multiplied by another half L, that's the moment. So this is that moment, okay? Live moment, this is L. So I have P live multiplied by L, and that's the live moment, okay? So the total moment, mu applied equal to 1.2 dead, which is MD, plus 1.6 live, which is ML. Okay, so that's the total applied moment. All right, so mu, oh, should I switch color? Mu, which is applied moment, equal to 1.2 md, right? So I'm going to write it out, and omega d L squared divided by 2 plus 1.6 ml, which is PL multiplied by L divided by 2. That's it. Okay, PL multiplied by L. Okay, so with that, let's proceed with the calculation. So mu equal to 1.2, and we said this is 300 pounds per foot. Okay, and I believe I have a 12 foot, so 20 foot at the span, so 20 feet. Okay, squared divided by 2 plus 1.6 and 5 kips. Okay, 5 kips multiplied by 20 feet. Okay, all right, so my math is not good, so gonna need help. Okay, so Noah.
Yeah.
Sir, can you help me out? What is the first term here? Can you punch the calculator for me to get the number for me, please? Horrible in this, okay? My math is not good.
Yeah, one sec.
Sure, no problem. Let me do on the side as well. 100 multiplied by 20 divided by, actually 20 again, divided by 2. So what number you got?
Is it 3,600?
3,600. Is this number good? Lucas, can you help me double check this number? This number good? The first term, 1.2 multiplied by this, right? Pay attention to here. Can you see it?
Yeah.
You check out to see if this number is correct.
Yeah.
All right. Got the same thing or different?
I got 72,000.
You got a 72,000, right? So
yes.
Somewhere I also got 72,000. Also got 72,000. Okay, Noah, can you double check to make sure?
Oh, yeah, I see what I did wrong. My bad.
All right, no problem. Okay, so we got that. Okay, so second term, this is simple, so I can do it myself. I got this value to be about 160. Okay, and 1, 2, 3. Okay, so that is the pounds, right? So this is pounds. foot. This is pound foot. Thank you, both of you. Thank you very much. And now MU, add them up together. I got, what is it, 1660. So 160 is a 2. I'm just going to wheel it. And there's a 3. And there's 232. And thousandths of cubic feet. Okay? Okay? Marshall, you there?
Yeah.
Can you help me check out if this number makes sense? Just simply add them together. Does that make sense?
Yeah.
Okay, good deal. Okay, thank you. So we're good. So that's a apply moment. Okay, that's a apply moment. So now we know how much moment we have to design for. Simply, we just need a VMM bigger than this value here. Okay, VMM bigger than this value here. So proceed, right? So how are we going to design it? How are we going to design it? So step number 1, AS. Okay, so we're going to assume it's yielded, right? Recall the procedure. Recall the procedure is going to go slowly here, back, sliding back where we were. Okay, so first use this equation, right? Use this equation. Okay, so recall AS, right, equal to MU, has to be bigger or larger than MU divided by phi Fy and D minus half A. Okay, but I don't know that. I don't know what A is. So write down equal to MU phi Fy JD. Okay, JD. So let's do a quick calculation. D, which is depth, that is height minus 2.5. So I got 24 inch minus 2.5, which is 21.5 inch. And JD equal to 90%, 0.9D, okay, 90%, okay? So I gotta get a number, 90% of that. Let's see what I got. I got 19.35 inch, okay? So that is my lever arm. So AS has to be bigger than equal than MU, which is 232 cubic foot, right? Cubic foot, I'm just gonna keep it here. And bottom here is 0.9 multiplied by 60 KSI yield strength and 19.35 inch. Jacob, Mr. Clemens.
Yes.
Can you help me out to get a number here? My math is really horrible.
Yeah, no problem.
Can you do that real quick? 232.
Is that 0.9 on the bottom?
Yes.
Okay.
Well, oh, that's a phi, right? That's assumed.
Yep.
Right? Okay. Punch in quickly. Check with my number.
Is it 0.22?
0.22, yes. Close. Okay, inch square, I'm just gonna save you the hassle, right?
All right.
All right? Is that right? Are you sure?
I'll track it again.
Okay, well, don't track again, right? Think about a unit, right?
Oh yeah, because yeah, convert.
Right, so I need to convert, right? So I just got to get a 12 foot.
Ooh, that's right.
Is that right? Can you redo it?
Yeah, I'll do that.
Okay, let's try it again. So 232 multiplied by 12. I'm doing the side only with 0. 232 multiplied by 12.
60 KSI and then times 19.35. So 2.66.
2.66, right?
Yes.
Let me check with my answer here. Yes. 2.66 inches square. Yeah, that sounds right. Okay, so that's the required steel. That's the required steel. Okay, so with this, what's the next step? What's the next step? I'm gonna check my compressive zone, right? I'm gonna check my compressive zone. So go back here, take a look. Right, so once we have the steel area, I need to check my compressive zone A, okay? And then get my C and finish the process, okay? So I'm gonna leave it like this. I'm gonna leave it like this because you see this in the homework as well, okay? You'll see this in the homework as well. So this will give you a head start. This will give you a head start on Thursday's homework. I think actually 36 for the first time, Jacob. Oh, okay, Jacob, okay. I think I made a mistake here, all right?
Either or I'm just mistaken, but I think it is 3,600.
Okay, I'll double check. Honestly, I ran a different set of number because the homework changed the bar size. Okay, but thanks.
I might not have converted, but I got 3,600.
Okay. Let me go back and check on that. Okay. But this is just to get you a head start. You see this like in the homework. You see this probably in the homework. Okay. Two things. The rest should be pretty straightforward. You can just follow the process we talked about last time. But the two things I want to clarify. One is location of the bars, right? We need to know which side of the bars here. Okay? All right. Second thing, when we calculate the dead load and live load, make sure you know the critical section for design. You know the critical section. Okay. All right. So any questions on the design of singular reinforced section? Any question about it?
I have a question.
Yes, sir.
Does D not change since the bars are on the top part of the concrete?
Okay. So good question, right? So now think about the section now, right? Actually, if it's inverted, right? The D is right here, isn't it? I mean, the bar is right here, the top, right?
Yeah.
So the D, the depth is defined from the compressive side to the tension side. So now this is called the D.
Okay.
Right? And now even a little more, so the compressive zone is right here. Right? This is the actual compressive.
Does everything flip then?
Yes, everything flipped.
Okay.
Got it?
Okay, thank you.
Okay, no problem. So you see this in tomorrow, from tomorrow's homework, and I'll run a review on this, okay? I try to finish this tomorrow on Thursday review so we can have some answer to go by. But if you want to get a head start, this is essentially the problem, okay? This is essentially the problem, all right? The cantilever section, okay? But in the exam, you see something different, okay? In the exam, you see something different. Not too much, but slightly different, all right? So any other questions we have on this, on the design of singular reinforced section? Any other questions? Okay, so one more thing. I have two students show up yesterday in the office hour. Granted, I was a little bit late, but we had a good conversation, solved some problems. So I strongly encourage you to come to the office hour on 2 o'clock, sorry, Tuesday, usually around 2 o'clock, but sometimes I run late because I have a meeting before. We can solve a lot of homework problems there together, okay? Now, I know you guys have group meet, fantastic work to work together to solve the homework. I like that. But I know sometimes you think less when you have a group chat. So if you can join me to solve the homework together on specific question, I would love to help you on that. Okay? All right. Okay. So that is the design for singular reinforced section. Today, actually, we're going to open up, okay, a little bit on how we design a doubly reinforced section right here, doubly reinforced section. Okay, so before we get started, I just want to rewind a little bit and review, right, the difference, just talked about it. The difference between singular and doubly is the compressive reinforcement. That means when you calculate the moment resistance, the compressive reinforcement also has contribution, so you have to count for it. Okay, and also we talk about this, right? There are one main reason why we need doubly reinforced section. We probably forgot by now, but just remind you, we need more ductility. We need more ductility, okay? So whenever we have a tension control case that the moment capacity is not there, and especially the ductility is not there, then we need doubly reinforced section. We need doubly reinforced section, okay? So now let's take a look at an example, right? Take a look at an example. So today is 7.1. Okay, lecture 7.1, okay? And this is for design of doubly reinforced section. Design of doubly reinforced section. Okay, design of doubly reinforced section. Okay, so to design a doubly reinforced section, we start a singular reinforced section, okay? So start from singularly reinforced section. Okay, we need to know whether the singular reinforced section will work. If it doesn't, we go to doubly. If it works, we're fine, right? So now here's my design problem. I got a 20 feet of span, 20 feet of span length, okay? And say this is N A, this is NB, okay? And I have a distributed load, Okay, this is omega D, that is 1.7 kip per foot. Okay, and I have a live load, omega LL live load, and that is 0.8 kip per linear foot. Okay, and given concrete strength for KSI, normal strength concrete, yield strength of the bar 60 KSI. Okay, and then number 4 stirrups. Number 4 stirrups. Okay, and I tell you that concrete covers 1.5 inch. Concrete cover 1.5 inch. Now I got people asking me about the concrete cover in the ACI. Okay, I said this before, so but I'm just gonna repeat. Okay, say that again. All right, so it's in 20.5.1.3. Okay, you can find the tables there. All right, so 20 ACI 20.5.1.3. Okay, you can find the detailing there. Okay, so that is the setup, right? That is the setup. Okay, and now one thing to make it easier, I say the soft weight of the concrete is included in the dead load. Okay, so you don't have to calculate the self weight, right? And I want to tell you that I need a section. I want to design a section, right? I want a section that H is smaller than 14 inch, okay? And I want a ratio between the height and the width approximately equal to 1. Very, very strict requirement, okay? I have some high requirement for my beam. All right, okay, so why I'm emphasizing this? Why I'm emphasizing this? I'll explain later, right? But you can see it's pretty stocky beam. The beam is not wide. The beam is not deep like we usually deal with. It's 1-to-1 ratio, right? Pretty squarish, okay? So that is one feature we have here, okay? And you know why we pick this, okay? But first of all, let's take a look at the section, right? Take a look at the section. So this is my requirement. So to make our life easy, I'm just gonna say, I give you a section, right? So select the section. Select the section, right? So I'm just gonna select the section with a dimension of H equal to 14 inch, okay? And B, which is the width of it, equal to 14 inch. Okay, so I want to get a depth first. Depth D equal to H minus the concrete cover, okay? And then, mind you that remember I have a beam, I have a bar here. So if the clear cover, this is clear cover by the way, is 1.5 inch, I need to have the bar, But I don't know the bar, right? So I'm just gonna assume number 8 bar. Okay, so this is dB divided by 2, number 8, so it's ½ inch divided by 2. ½ inch divided by 2. So roughly D equal to what? 14 minus 0.5 minus 0.5 inch divided by 2. That gives me what? This is 1.275, so it's about 12.275. Let me double check. I feel my numbers a bit different. 14 minus 1.5.
Why did you do ½ inch over 2 instead of an inch over 2?
I just assume it's not, oh, sorry. Yeah, you're right. I got the other thing. Right, so this is 1 inch, number 8, right? 1 inch divided by 2. Okay, but okay, I think I forgot one thing. It's the stirrup size right here. Right. That's why I got a mixed number. Okay, so this is my bar. Okay, I got my stirrups right here. Okay, so I have the clear cover from concrete to the stirrups 1.5 inch. I have to count for the stirrups. That's where I messed up, I think, which is number 4, so 0.5 inch. Okay, and I have to count for the half bar, dB divided by 2. Okay, so this makes sense. So minus stirrup 0.5 inch. Yeah, this makes sense. So I have now this is 0.75. Yes. Okay. Is it clear now? So I have stirrups 1.5 and concrete cover minus 0.75. Yes, I got 11.75 inch as the depth of my beam. Okay, so that is the depth of my beam. All right, so now I have a geometry that is fixed. I have a height of 14 inch, width of 14 inch, and depth of 11.75 inch. So that's the cross section. So assume I'm going to have singular reinforced section. So first, I'm just going to determine my nominal moment capacity required, right? Nominal moment capacity required. So MU, okay? What is MU, right? So omega U, which is a dead load, right? Omega U here equal to 1.2 omega dead.
Bob,
Yes.
sorry. Wouldn't that be for the depth? Wouldn't that be 2.5 inches total that we're subtracting? So it would be 11.5 instead of 11.75.
Did I get it wrong? Let me redo it. Okay, so 14 minus 1.5 minus 0.75. No, I think I got 11.75, isn't it?
Where did we get the 0.75 from?
This is ½ inch bar size.
Right.
Stirrups.
Isn't that also ½ inch?
Yeah, that's 0.5. Oh, you know what? Messed up today. Pretty bad. Sorry about that. You're right. So 0.5. This is 1 essentially, right?
Yeah.
You got it. You're right.
Okay, thank you.
Oh, you're right. Thank you. Yeah, I know I made the math yesterday here because I changed my geometry again. Okay, wait 1 second. Let me make sure I got it right. So 14. Yes. Is it better now?
Yep, thank you.
Sure. No, thank you. Appreciate that. Okay. Yes. Sorry about this fumbling. Okay, I changed the geometry last minute. That's what I get. Okay. All right. Anyhow, so let's get back to the apply moments. Okay, MU here. So before I get MU, I need my distributed load. So omega U to 1.2 dead plus 1.6 live. Okay. So carry on. The dead load is 1.7 kips per foot, and the live load is 1.6, 0.8 kips per foot. Okay, and I got a total applied load equal to 3.32 kips per linear foot. Okay, and that is the distributed load, total distributed load. So MU, which is the simply supported beam, so that is omega U L squared divided by 8. L squared divided by 8. So that is 3.32 multiplied by L 20 feet squared divided by 2. And I got this number to be 166 kip foot. Okay, kip foot. All right, so I know my applied moment is 160 kip foot. So all I have to do is make sure my VMN is bigger than this number here. Right, it's not too bad, not too bad. All right, so first step, design as singularly reinforced section first. Okay. Design as singularly reinforced section first. Okay, so here's a trick. How we're going to design a singular reinforced section? Singular reinforced section. Okay, nothing is known. So I'm going to do this. Okay, this is something new. Okay, there's a tension controlled reinforced limit. Tension controlled reinforced limit. Okay, that is the reinforcement ratio defined rho. Okay, rho as AS divided by BD. Okay, and this actually has the equation 0.85 beta 1. Okay, F prime C Fy, F prime C Fy, and here is 0.003. Okay, on the top 0.03 plus 0.005. So we ask, where is 0.03 coming from? This is epsilon Cu. Okay, and this 0.05 is tension control strain limit. Okay, so that means if I provide steel with this much reinforcement ratio, I naturally will achieve a tension controlled case. Okay, so now let's bring the number in. Let's see what we have here. Bring the number in what we have here. Okay, first of all, it's 4 KSI concrete. So F prime C equal to 4 KSI. So F B beta 1 equal to 0.85. Okay, so rho TC tension control equal to 0.85 multiplied by 0.85 multiplied by top of 4 KSI concrete and yield strength of 60 KSI. Okay, and then top here is 0.003 plus 0.008. Okay, and I got this number to be roughly 0.018. I got 4 more minutes. Okay. So this is the tension control reinforcement ratio. So once I have this ratio, I'm to convert to reinforcement area AS equal to BD multiplied by rho TC. Okay, so that is B is 14 inches, right? And what is my depth? 11.5 inches, right? Okay, and 0.018. That is the ratio. So that is the area, right? So I got 2.9 inch squared. Okay, 2.9 inch squared. So A, effective depth equal to ASFY divided by 0.85 F prime CB. Okay, so that is 2.9 inch squared, 60 KSI, divided by 0.85 F prime C is 4 KSI, and width is 14 inches. Okay, so eventually my effective compressive zone A equal to 3.66 inch. Okay, 3.66 inch. So with that, I will proceed without any check and balance. Okay, so this is not a full design of single reinforced section. It's just a quick check. Okay, so with that, I'm gonna get my nominal moment capacity equal to ASFY. All right, here depth D minus half A. Okay, so AS is 2.9 inch squared, FY 60 KSI. And depth is 11.5 minus 3.66 inch divided by 2. And I got this number to be MN equal to 1683 kips inch. So I want to convert that to a foot. Let me do it real quick. 1683 divided by 12. I got 140.25 kip feet. Okay. So now, since it's tension controlled, I assume, well, I force it to be tension controlled to begin with, so phi equal to 0.9. Okay, so phi mn equal to 0.9 multiplied by 140.25 kip foot. Okay, so after this reduction, I got, what is the number I have? I got, 140 multiplied by 90% reduction. 126 foot. Okay, so apparently this number is not adequate. It's smaller than the applied moment, which is right here, 166. Okay, 160 foot. So I know that this is inadequate. This is inadequate. Now, I have choices, right? Keep in mind, right now it's 2.9 inch squared, 2.9 inch squared, all right? So I look at the section. It's a pretty stocky section. I have only a 14 inch width, okay? Very narrow beam. And I have I have AS required for tension control is about 3 inch squared. So on the stack 3, number 9 bars. Okay, to satisfy, right? So I have this is number 9 bar, I have 3 number 9 bars. Okay, and if this does not satisfy the required moment capacity, I have to keep piling up more. But you realize that this direction is also 14 inch. Okay, so that will cause a problem. What type of problem? Eventually, the bottom bar will be too many, and I have a neutral axis that is too thin or too short. Okay, so if we go on with this case, if increase bars, I have no sufficient or insufficient space to put them. Okay, and that's when we're going to design as a doubly reinforced section. Okay. And I'm in this awkward situation just because I selected geometry that the height and width ratio is 1 to 1. If the height and width ratio is larger than that, I should be able to get away by piling more singular reinforcement at the bottom here. But I messed up. I have a stacky section to start with. I have limitations, restrictions. Okay, so take it away as usually doubly reinforced section for wide beam, okay, for wide beam. Okay. All right, okay, I think this is a good stop. We're gonna continue on Thursday, tomorrow, we just talk about the rest part of it and circle back and review some of the problems you might face. So far, we haven't decided yet still about the exam format. Probably give another week. We'll let you know when it's going to be what is the exam format. But in terms of content, we're pretty set on the content. So the first exam, okay? First exam. It's going to be on flexure, okay? Everything bend, everything bend, okay? Everything bend. So we talk about the singular reinforced section. That is, you can start review sets process now. Singly, doubly, both analysis and design. Analysis, design. And for the next couple of weeks, we'll talk about irregular sections, and T-beam. Okay, so this will be the content for the first exam. Okay, this will be the content for the first exam. All right, any questions, guys? Any question, guys?
Yeah, could you scroll